Deep in the Atacama Desert, the most powerful radio telescopes on Earth capture whispers from the universe's infancy. What they've found challenges everything we thought we knew about the beginning of time itself. The cosmic microwave background, that faint afterglow of the Big Bang, contains patterns that weren't predicted by any standard model. These anomalies suggest something unprecedented. Our universe might not be the first. Tonight, we explore evidence that reality itself might be cyclical, with universes being born, dying, and reborn in an infinite cosmic dance. What if our universe is just the latest in an infinite series? The story begins 13.8 billion years ago, or so we thought. In 1965, Arno Penzias and Robert Wilson discovered what they initially considered an annoying hiss in their radio antenna. This cosmic static turned out to be the most important discovery in modern cosmology: the cosmic microwave background radiation. This radiation represents the universe's baby picture, a snapshot taken when it was only 380,000 years old and hot enough to glow. For decades, this discovery seemed to confirm our linear view of cosmic history. The universe began with the Big Bang, expanded and cooled, formed the first atoms, then stars, galaxies, and eventually us. Case closed, or so it seemed. But as our instruments became more sensitive, unexpected patterns emerged from this cosmic background. The Wilkinson Microwave Anisotropy Probe, launched in 2001, revealed temperature fluctuations that didn't match theoretical predictions. These weren't random variations but structured patterns, as if the universe retained memory of something that came before. The most striking discovery came from the Planck satellite, which mapped the cosmic microwave background with unprecedented precision. The data revealed what cosmologists call the cold spot, a region where the temperature is significantly lower than the surrounding areas. This wasn't just an interesting anomaly. According to standard cosmology, such a feature shouldn't exist. The early universe should have been remarkably uniform, with only tiny fluctuations that would later grow into galaxies. But the cold spot is too large and too cold to be explained by conventional physics. Some researchers suggest it might be a void, a massive empty region of space. Others propose more exotic explanations. It could be evidence of a collision between our universe and another. Dr. Laura Mersini-Houghton at the University of North Carolina has spent years analyzing these anomalies. Her research suggests the cold spot might be a cosmic bruise, a scar left by our universe's interaction with another universe before the Big Bang. This idea challenges our fundamental understanding of cosmic beginnings. If true, it means our universe didn't emerge from nothing but from the collision or interaction of pre-existing cosmic structures. The implications are staggering. If universes can collide and interact, what does that tell us about the nature of reality itself? Another puzzling feature in the cosmic microwave background is what astronomers call the axis of evil. This isn't a reference to moral philosophy, but to an unexpected alignment in the cosmic background radiation. Large-scale structures in the universe appear to be aligned with our solar system's ecliptic plane. This alignment is so unlikely that it challenges the cosmological principle, the assumption that the universe looks the same in all directions. The odds of this alignment occurring by chance are astronomically small. Some cosmologists argue this might be evidence of a preferred direction in the universe, possibly inherited from a previous cosmic cycle. These anomalies have forced physicists to reconsider fundamental assumptions about cosmic origins. Perhaps the Big Bang wasn't the beginning but a transition, a moment when one cosmic cycle ended and another began. This possibility brings us to one of the most radical ideas in modern cosmology, the cyclic universe. The concept isn't entirely new. Ancient Hindu cosmology described infinite cycles of creation and destruction, with each universe lasting billions of years before being reborn. But modern physics has given this ancient wisdom a scientific framework. The cyclic universe model suggests that what we call the Big Bang was actually a big bounce, the moment when a contracting universe reached its minimum size and began expanding again. This model requires exotic physics, including negative energy and quantum effects at cosmic scales. But it offers elegant solutions to several cosmological puzzles. Why is the universe so flat? Why is it so uniform? Why do the physical constants seem fine-tuned for life? A cyclic universe could naturally explain these features through an endless process of cosmic evolution and selection. Each cycle would refine the universe's properties, gradually approaching the conditions we observe today. The theoretical framework for cyclic cosmology emerged from string theory and higher-dimensional physics. In this model, our three-dimensional universe is like a membrane floating in higher-dimensional space. These membranes can collide, creating the conditions for a new Big Bang. The collision would generate the hot, dense state that we observe as the cosmic microwave background. But unlike the traditional Big Bang, this collision would preserve information from the previous cycle. This information might manifest as the anomalies we observe in the cosmic background radiation. The cyclic model also predicts specific patterns in gravitational waves, the ripples in spacetime caused by cosmic events. These waves would carry signatures of the previous universe, encoded in their frequency and amplitude. The Laser Interferometer Gravitational Wave Observatory, or LIGO, has already detected gravitational waves from colliding black holes and neutron stars. Future detectors might be sensitive enough to detect the primordial gravitational waves from the Big Bang itself. If these waves carry signatures of pre-Big Bang physics, it would provide direct evidence for the cyclic universe theory. The search for these signatures has become one of the most exciting frontiers in modern cosmology. Meanwhile, other researchers are looking for evidence in the cosmic web, the large-scale structure of the universe. Computer simulations of cosmic evolution can reproduce the observed distribution of galaxies and dark matter. But these simulations require precise initial conditions, the seeds from which all cosmic structure grew. In the standard model, these seeds are assumed to be random quantum fluctuations. But a cyclic universe might inherit more complex initial conditions from the previous cycle. These inherited structures could explain why the universe appears to be more organized than random fluctuations would suggest. The quest to understand cosmic origins has led to increasingly sophisticated observations and theories. The James Webb Space Telescope, launched in 2021, is already providing new insights into the early universe. Its infrared vision can peer through cosmic dust to observe the first galaxies and stars. These observations will test our understanding of how structure formed in the early universe. If the cyclic model is correct, the first galaxies might show unexpected properties inherited from the previous cosmic cycle. The search for these signatures requires careful analysis of subtle patterns in the data. But the potential payoff is enormous. Direct evidence that our universe is part of an infinite cycle of cosmic death and rebirth. This possibility has profound implications for our understanding of reality itself. If universes can die and be reborn, what happens to the information they contain? Do the laws of physics remain constant across cosmic cycles? Could life itself be part of this eternal cosmic dance? These questions bring us to the heart of modern cosmological mystery. The cosmic microwave background, once seen as proof of a single cosmic beginning, now hints at a far more complex reality. We may be living in just one verse of an infinite cosmic symphony. The next movement in this symphony might already be written in the patterns of ancient light that surrounds us. As we continue to decode these cosmic messages, we edge closer to understanding our place in the eternal dance of creation and destruction. The universe, it seems, has been keeping secrets. In 2020, Roger Penrose won the Nobel Prize in Physics for his work on black holes. But his most controversial theory doesn't involve black holes at all. It's about what happens after the universe dies. Penrose's conformal cyclic cosmology proposes that our universe is destined to expand forever, growing cold and empty. Most stars will burn out, black holes will evaporate, and only photons will remain, traveling through empty space. In this far future, the universe will have no matter, no scale, and no time. And according to Penrose, this is exactly the condition needed for a new Big Bang. The idea seems paradoxical, but it's rooted in sophisticated mathematics. Penrose realized that a universe containing only massless particles looks identical to the earliest moments after the Big Bang. Both states have no natural length scale, no way to measure distance or time. This mathematical equivalence suggests that the end of one universe could become the beginning of another. The transition would be seamless, with no boundary between death and rebirth. Unlike other cyclic models, Penrose's theory doesn't require exotic physics or extra dimensions. It works within the framework of general relativity and quantum mechanics. The key insight is that the universe's geometry can be stretched and compressed without changing its essential properties. This process, called conformal transformation, allows the infinite future of one universe to become the finite past of another. But if this is true, we should be able to find evidence of previous cosmic cycles in the cosmic microwave background. Penrose and his collaborators have spent years searching for these signatures. They've identified several features that might be remnants of the previous universe. The most striking are circular patterns in the cosmic background radiation. These circles appear where massive objects from the previous universe have left their gravitational imprint. The patterns are subtle, barely visible above the cosmic background noise. But statistical analysis reveals they're more common than chance would predict. Critics argue that these patterns could be explained by known physics. The cosmic microwave background contains many random fluctuations, and some of them will inevitably form circular patterns. But Penrose's team has responded with increasingly sophisticated analysis. They've identified not just circles but specific types of circles, with properties that match the predictions of conformal cyclic cosmology. The debate continues, but the observations are pushing the boundaries of what we can learn from the cosmic microwave background. Another piece of evidence comes from the universe's overall geometry. Observations suggest that space is remarkably flat, with no detectable curvature. This flatness is unexpected in a universe that began with a Big Bang. Random initial conditions would more likely produce a curved universe. The cyclic model offers a natural explanation. The universe has been flattened by previous cycles of expansion and contraction. Each cycle would remove some curvature, gradually approaching the flat geometry we observe. This process would also explain why the universe's expansion is accelerating. Dark energy, the mysterious force driving this acceleration, might be a remnant of the previous universe's collapse. The mathematical framework for this idea is complex, involving quantum field theory and general relativity. But the basic principle is elegant. The universe recycles its own energy, using the remnants of death to fuel new life. This recycling process might also explain one of the deepest mysteries in physics, the arrow of time. Why does time flow in one direction? Why do we remember the past but not the future? These questions have puzzled physicists for generations. The laws of physics are symmetric in time, meaning they work equally well forward or backward. Yet our experience of time is decidedly asymmetric. The cyclic universe offers a potential solution. If the universe goes through repeated cycles of expansion and contraction, the arrow of time might be reset with each cycle. The direction of time would be determined by the direction of cosmic expansion. During expansion, time flows forward. During contraction, it might flow backward. This idea has profound implications for the nature of consciousness and memory. If time can flow backward, what happens to the information stored in our brains? Do we experience reverse time, or do we simply cease to exist? These questions touch on the deepest mysteries of existence itself. The cyclic universe model also addresses the problem of cosmic fine-tuning. The physical constants of our universe appear to be precisely calibrated for the existence of stars, planets, and life. Change any of these constants by a small amount, and the universe would be uninhabitable. This apparent fine-tuning has led some to suggest that our universe was designed by an intelligent creator. But the cyclic model offers a naturalistic explanation. If the universe goes through infinite cycles, it would naturally evolve toward life-friendly conditions. Each cycle would test different combinations of physical constants. Only those cycles that produce stable structures would survive long enough to begin the next cycle. Over time, this process would select for universes capable of supporting complexity and life. The math that underlies this selection process is still being worked out. But the basic idea is similar to biological evolution: random variation followed by selection. The universe doesn't need to be designed. It can evolve. This evolutionary perspective on cosmology opens new avenues for research. Instead of asking why the universe has the properties it does, we can ask how it acquired them. The answer might lie in the cosmic history that stretches back through countless previous cycles. Each cycle would leave its mark on the next, creating a chain of cosmic inheritance. The properties we observe today might be the result of this long evolutionary process. But proving this requires more than theoretical speculation. We need observational evidence that the universe has indeed gone through multiple cycles. The search for this evidence has led to some of the most ambitious projects in modern astronomy. The Laser Interferometer Space Antenna, or LISA, will be the first space-based gravitational wave detector. Scheduled for launch in the 2030s, LISA will be sensitive to gravitational waves with much lower frequencies than current detectors. These low-frequency waves could carry signatures of the Big Bang itself. If the Big Bang was actually a big bounce, the gravitational waves would have a distinctive spectrum. The waves would be enhanced at certain frequencies, creating a pattern that could distinguish between different cosmological models. The European Space Agency's Euclid mission, launched in 2023, is mapping the three-dimensional structure of the universe. This map will reveal how galaxies are distributed on the largest scales. If the universe is cyclic, this distribution might show patterns inherited from previous cycles. The search for these patterns requires analyzing the positions and motions of billions of galaxies. Advanced computer algorithms are being developed to identify subtle correlations that might indicate cosmic recycling. Meanwhile, theorists are working to refine the mathematical framework of cyclic cosmology. The equations that describe the transition from one cycle to the next are extraordinarily complex. They involve quantum field theory, general relativity, and aspects of string theory. Understanding these equations requires pushing the boundaries of theoretical physics. New mathematical tools are being developed to handle the infinite dimensional spaces that arise in these calculations. The results are beginning to make testable predictions about the structure of the cosmic microwave background. These predictions will be tested by future observations, providing a way to distinguish between different models of cosmic evolution. The stakes couldn't be higher. If the cyclic universe is real, it would revolutionize our understanding of reality itself. We would live in a universe that has no beginning and no end, only eternal transformation. Death and birth would be two sides of the same cosmic coin. The implications for human existence are profound. If the universe is eternal, does that mean we've lived before? Will we live again in future cycles? These questions go beyond physics into philosophy and theology. They challenge our most basic assumptions about the nature of existence. The cyclic universe doesn't just change how we think about the cosmos, it changes how we think about ourselves. We are not just products of a single cosmic accident, but participants in an eternal dance of creation and destruction. Our atoms were forged in the hearts of stars that died billions of years ago. But those stars themselves might have been formed from the remnants of previous cosmic cycles. In this view, we are not just stardust but cosmic dust, carrying the memory of infinite universes. The search for evidence of previous universes continues with ever-increasing sophistication. Each new observation brings us closer to understanding the deepest mysteries of existence. The cosmic microwave background, once thought to be a simple afterglow of creation, now appears to be a complex palimpsest. Written over and over again, it contains the stories of countless cosmic cycles. We are beginning to learn how to read these stories, to decode the messages left by previous universes. The process is slow and painstaking, requiring the most advanced technology and mathematics. But with each discovery, we gain new insight into the nature of reality itself. The universe, it seems, is far stranger and more wonderful than we ever imagined. And we've only just begun to explore its infinite depths. Black holes are cosmic monsters, devouring everything that falls within their gravitational grasp. Even light cannot escape their pull. But what happens to the information that falls into these cosmic voids? This question has haunted physicists for decades, and the answer might hold the key to understanding how universes recycle themselves. The problem began with Stephen Hawking's discovery that black holes emit radiation. This radiation, now called Hawking radiation, slowly evaporates black holes over enormous timescales. But this radiation appears to be completely random, carrying no information about what fell into the black hole. This creates a paradox. If information is truly lost when black holes evaporate, it would violate one of the fundamental principles of quantum mechanics. Information, according to quantum theory, cannot be destroyed. It can be scrambled, hidden, or transformed, but never eliminated. The resolution of this paradox might explain how universes preserve information across cosmic cycles. Recent breakthroughs in string theory and quantum gravity suggest that information is not actually lost. Instead, it's encoded in the black hole's event horizon, the boundary beyond which nothing can escape. This information might be released when the black hole evaporates, but in a form so scrambled that it appears random. The mathematical framework for this process is extraordinarily complex. It involves quantum entanglement, holographic principles, and the strange geometry of higher dimensional space. But the basic idea is that information can survive even the most extreme cosmic catastrophes. If this is true, then information from our universe might survive its eventual heat death. The cosmos might be like a vast computer processing information through cycles of expansion and contraction. Each cycle would be a computation, exploring different possible arrangements of matter and energy. This computational view of the universe has profound implications for our understanding of reality. If the universe is computing, what is it computing? Some theorists suggest it might be exploring all possible ways of organizing information. Others propose it's solving some cosmic optimization problem, finding the best way to arrange matter and energy. The answer might be written in the patterns we observe in the cosmic microwave background. These patterns might be the output of cosmic computation, the results of billions of years of information processing. The search for these computational signatures has led to new ways of analyzing cosmological data. Instead of looking for specific patterns, researchers are studying the information content of the cosmic background radiation. They're using tools from information theory, the mathematical framework that underlies computer science and communication. These tools can measure how much information is contained in the cosmic microwave background. If the universe is computational, this information content should follow specific patterns. The preliminary results are intriguing. The cosmic microwave background contains more information than would be expected from random quantum fluctuations. This excess information might be the signature of cosmic computation. But proving this requires distinguishing between different sources of information. Some of the excess might come from known physical processes, like the formation of the first stars. Other parts might be genuine remnants of cosmic computation. The challenge is developing tools sensitive enough to make this distinction. Meanwhile, the discovery of gravitational waves has opened an entirely new window on the universe. These ripples in space-time carry information about the most violent events in cosmic history. When two black holes merge, they create gravitational waves that can be detected billions of light-years away. The pattern of these waves reveals the masses and spins of the merging objects. But if the universe is cyclic, these waves might carry additional information. They might contain echoes of gravitational waves from previous cosmic cycles. The search for these echoes requires extremely sensitive detectors. Current gravitational wave observatories are already pushing the limits of measurement precision. They can detect changes in distance smaller than 1/10,000th the width of a proton. But detecting primordial gravitational waves requires even greater sensitivity. The next generation of detectors, including space-based observatories, might be able to detect these faint signals. The European Space Agency's LISA mission will be the first space-based gravitational wave detector. Its 3 spacecraft will form a triangle with sides millions of kilometers long. This enormous scale will make it sensitive to gravitational waves with periods of minutes to hours. These low-frequency waves could carry signatures of cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang. But if the Big Bang was actually a big bounce, the gravitational wave spectrum would be different. The waves would show evidence of the collision or transition that marked the end of the previous cycle. This difference could provide definitive evidence for the cyclic universe model. The theoretical predictions for these gravitational wave signatures are becoming increasingly precise. Computer simulations can model the collision of cosmic membranes, the process that might create a new universe. These simulations require enormous computational resources, using some of the world's most powerful supercomputers. The results show that membrane collisions produce distinctive patterns in gravitational waves. These patterns would be like fingerprints, uniquely identifying the cyclic universe model. The search for these fingerprints has become one of the most exciting frontiers in experimental physics. But the cyclic universe raises profound questions about the nature of time itself. If the universe goes through infinite cycles, what does that mean for causality? Can events in one cycle influence events in the next? The mathematics of cyclic cosmology suggests that information can indeed pass between cycles. This information might be encoded in the fundamental constants of physics. The strength of gravity, the mass of the electron, the speed of light, these constants might be set by the history of previous cycles. This idea has revolutionary implications for our understanding of natural laws. Instead of being fixed and eternal, the laws of physics might evolve over cosmic time. Each cycle would test different combinations of physical constants. Only those combinations that produce stable, long-lived universes would survive to the next cycle. Over infinite time, this process would select for universes capable of supporting complexity and life. We might be living in a universe that has been fine-tuned not by design but by evolution. This evolutionary perspective on cosmology has attracted interest from philosophers and theologians. It offers a naturalistic explanation for the apparent fine-tuning of the universe. But it also raises new questions about the nature of existence. If the universe is eternal, does that mean we've lived before? Will we live again in future cycles? These questions touch on deep issues of personal identity and consciousness. The cyclic universe model suggests that the information that makes us who we are might persist across cosmic cycles. but it would be scrambled and transformed in ways we can barely imagine. We might be reincarnated not as individuals, but as patterns in the cosmic web. Our thoughts and memories might be encoded in the structure of space-time itself. This possibility has inspired new research into the nature of consciousness and information. Some theorists propose that consciousness might be a fundamental feature of the universe. If so, it might persist through cosmic cycles, evolving and adapting to new conditions. The search for evidence of cosmic consciousness is still in its infancy. But the tools of modern physics might eventually allow us to detect its signatures. The cosmic microwave background, gravitational waves, and the large-scale structure of the universe all carry information about the deepest levels of reality. As our instruments become more sensitive, we might discover that the universe is not just a collection of particles and fields, but a vast information processing system. This system might be conscious in ways we can't yet understand. The cyclic universe model also has implications for the future of humanity. If the universe is eternal, then life might have infinite opportunities to develop and evolve. The death of one universe would not be the end but a transformation. Life might find ways to encode itself in the fabric of space-time, surviving the transition between cycles. This possibility has inspired research into digital immortality and consciousness uploading. If we can understand how information is preserved across cosmic cycles, we might learn to preserve ourselves. The technology for this kind of preservation is still far beyond our current capabilities. But the theoretical framework is beginning to emerge from studies of quantum information and cosmology. The key insight is that information can exist independent of its physical substrate. Just as a song can be encoded on a CD, vinyl record, or digital file, consciousness might be encoded in different forms of matter and energy. The challenge is learning how to read and write this cosmic code. The search for previous universes has become a search for the deepest truths about reality. Each new observation brings us closer to understanding the nature of existence itself. The cosmic microwave background, once seen as a simple afterglow of creation, now appears to be a complex message from the past. This message might contain the history of countless cosmic cycles. We are beginning to learn how to decode this message, to read the stories written in the patterns of ancient light. The process is slow and painstaking, requiring the most advanced technology and mathematics. But with each discovery, we gain new insight into the nature of reality itself. The evidence for previous universes is still circumstantial, based on subtle anomalies and theoretical predictions. But the accumulation of evidence is beginning to paint a consistent picture. The universe appears to be stranger and more wonderful than we ever imagined. Instead of being a single, finite event, cosmic history might be an infinite story of death and rebirth. We are characters in this story, made from the recycled atoms of countless previous universes. Our consciousness might be a pattern that has existed before and will exist again. The implications are both humbling and inspiring. Humbling because they remind us that we are just small parts of an infinite cosmic process. Inspiring because they suggest that this process might be conscious and purposeful. The universe might not be a random accident, but a vast mind exploring its own possibilities. We might be thoughts in this cosmic mind, experiencing reality from the inside. This perspective changes how we think about our place in the cosmos. We are not just observers of the universe, but participants in its self-discovery. Every scientific discovery is the universe learning about itself. Every moment of consciousness is the cosmos becoming aware of its own nature. The search for evidence of previous universes is therefore a search for self-knowledge. We are the universe trying to understand its own history. The cosmic microwave background is the universe's memory, and we are learning to read it. The gravitational waves are the universe's heartbeat, and we are learning to feel it. The large-scale structure of galaxies is the universe's anatomy, and we are learning to map it. Through science, we are becoming the universe's nervous system, connecting its parts and allowing it to sense itself. This process of cosmic self-discovery is just beginning. The next generation of observatories will probe deeper into space and time than ever before. The James Webb Space Telescope is already revealing the universe's infancy with unprecedented clarity. Future telescopes will be even more powerful, capable of detecting the faintest signals from the cosmic dawn. These observations will test our theories about cosmic cycles and universal consciousness. They will either confirm our emerging understanding or force us to develop new theories. Either way, they will deepen our appreciation for the mystery and beauty of existence. The universe is not just a collection of matter and energy, but a story being told across infinite time. We are both the characters and the authors of this story. Through our observations and theories, we are writing the next chapter. The story of the cyclic universe is a story of hope. It suggests that death is not the end but a transformation. It implies that information and consciousness can survive even the most extreme cosmic catastrophes. It offers the possibility that we are part of an eternal process of growth and discovery. Whether or not the cyclic universe is real, it has already changed how we think about existence. It has shown us that the universe is far stranger and more wonderful than we ever imagined. It has revealed the deep connections between physics and philosophy, between cosmology and consciousness. It has reminded us that we are not separate from the universe but integral parts of it. As we continue to search for evidence of previous universes, we are really searching for ourselves. We are trying to understand our own nature and purpose. The cosmic microwave background, with its subtle patterns and mysterious anomalies, might be the universe's way of telling us who we are. We are recycled stardust, made from the atoms of countless previous cycles. We are information patterns encoded in the fabric of space-time itself. We are the universe's way of knowing itself, of experiencing its own beauty and complexity. The search for previous universes is therefore the most important quest in science. It is a search for the deepest truths about reality, consciousness, and existence. It is a journey that will take us to the very limits of human knowledge and imagination. And it is a journey that has only just begun. The universe, it seems, still has many secrets to reveal. And we are just beginning to learn how to listen to its ancient wisdom. In the end, the question of whether we've found evidence of a previous universe might be less important than the journey itself. The search has already revealed the profound interconnectedness of all things. It has shown us that we are not isolated beings but part of an infinite cosmic story. It has taught us that the universe is not just a place but a process, not just matter but meaning. Whether or not previous universes exist, we are undoubtedly part of something far greater than ourselves. And that realization, perhaps, is the most important discovery of all. The cosmic dance continues, and we are privileged to be part of it. We are the universe awakening to its own infinite beauty. And that awakening has only just begun.